Now let's discuss the other way scientists know the age and the timeline of Earth's long history. This is called absolute dating. Okay, so scientists have a way of determining the actual age of a fossil. Scientists do this by looking at the properties of atoms contained in the fossil. So generally, this is referred to as radiometric dating, also known as radioactive dating. Both mean the same thing, and they are a type of absolute dating. When fossils are created, or when animals are alive, I should say, they all have a few atoms that are radioactive. Now, this means that the atoms will at some point shoot off parts or energy into their surroundings. After doing this, they are no longer radioactive. This is called radioactive decay. Now, when there are a lot of these atoms, like in a nuclear reaction, this is harmful, or it can cause cancer or other illnesses. But in normal rocks, normal fossils, and other things, there are just too few to be unhealthy. We should also know that scientists measure the amounts of atoms that are radioactive and non-radioactive in a fossil. So a fossil that has more radioactive atoms will be younger. And because atoms decay over time, a fossil will gradually have less and less radioactive atoms as it gets older. Scientists must also know how fast atoms of a particular type are decaying. Okay, this is commonly referred to as a substance's half-life. Now this is known, this is public knowledge, this is something that you can Google, for instance. You can Google half-life of carbon-14, for instance. And when you know the rate at which it decays, now we can tell the age of something by measuring how fast those radioactive atoms in a particular fossil are decaying and how much has decayed at this point. Let's take a look at an example of how a scientist might use the measured amounts and knowledge of half-life to determine the age of a fossil.
Well, let's talk about the time it takes for an isotope to decay, what's known as its half-life. And the half-life is the time it takes for half, or 50%, of the amount of isotope to decay. And in the example of carbon-14, it's been measured to take about 5,730 years for half of the amount of carbon-14 in a sample to decay. Well, right now, our cow is a living organism, and so it's going to have 100% of the carbon-14 that it will ever have as it takes in carbon from eating plants, as we just mentioned on the previous slide. But look at the first layer buried underneath the ground. And this is a fossil of a horse. Let's pretend that this fossil was discovered and it has 50% of the carbon-14 as those living today. Well, we would say that one half-life has passed, which we know is 5,730 years, and so we would say that this horse, or this fossil of the horse, is 5,730 years old. But look at the next fossil beneath it. Let's pretend this fossil is found and is discovered to have 25% of the carbon-14 remaining. Well, 25 is half of 50, and 50 is half of 100. So 2 half-lives have passed since this organism was alive. So 2 times the half-life of 5,730, this fossil would estimate to be about 11,460 years old. Well, let's go ahead and plot this information in a graph. And what you see in the graph is exactly what we just talked about. You can see at 50%, if a sample has 50% of the carbon-14 remaining, it would estimate to be about 5,730 years old. If a sample has 25% of its carbon-14 remaining, it would estimate to be 11,460 years old. If a sample has 12.5% of its carbon-14, it would estimate to be 17,190 years old. Well, now this is great for the data that we just talked about, but what if there's something that is discovered that is in between? Well, let's look at that. What if a fossil is found to have 70% of its carbon-14 remaining? Well, this is where you can see the beauty of a line graph. We can just kind of estimate by drawing an imaginary line down, and we would say, oh, if it has 70% of its carbon-14 remaining, it would be roughly around 3,000 years old, give or take a few years, of course. What if a fossil is found to have 20% of its carbon-14 remaining? Well, then if we draw an imaginary line down, we would say, oh, that's about 14,000 years old. So you can see with the decay rate of carbon-14, we can roughly estimate with pretty good accuracy the ages of fossils.